Hi, everybody. I'm Tom, as everyone mentioned. Sorry? Okay, so stone, yeah. It's actually a quote by Nietzsche. He was right, but from all the wrong reasons, I guess. He was very reluctant to insert new technologies, and I think a lot of his philosophy was his way to react to new technologies. So I'll try to resolve this conflict, at least, by telling you a short story, about Grabowski and Sons. Whoever is not Israeli might know us, not know us, but they have a stone factory next to Jerusalem. They're third generation of stonemakers in Jerusalem. They have a quarry down south. And these guys established the Israeli Stone Quarries Organization 10 years ago. There were 10 companies, but today there's only one. And it's Grabowski and Sons. Essentially, they're the only one to survive. And this is due to a lot of competition from China, from new materials, and from the loss of the craft. Now, our region has a very long history of using stone as a central architectural element. This is from Konrad Schick, an architect and archaeologist who worked in Jerusalem in the 19th century. He describes the chisel marks on what he called Solomon's quarries in Jerusalem. It's Zedekiah's cave, Me'arat Tzidkiyahu, and these are the chisel marks. Now, Tawfiq Knan, he was actually head of the Hansen Hospital, designed by Konrad Schick. And Tawfiq is a Palestinian doctor, but he also describes in detail the tools used by stone craftsmen at the early 19th century. These are essentially the same tools used today. And this legacy is still present in the master plan for Jerusalem, in which it stated that the outer walls and pillars of houses will be covered with natural, finely dressed stones. And the Standard Institution of Israel references traditional stone dressing methods and provides a very detailed account to the different patterns of stone finishing in its texts. Now, I hope this is not too strong, but in a recent visit to Grabowski's factory, it's a very loud craft stone. There were signs that in recent decades, the stone industry had undergone this transformation towards the automation of production processes. But if you look closely enough at each stone process, at least at its end, you'll see still the demand for skilled stone craftsmen to carry out very complex custom tasks. And as the craft stone is one that is traditionally passed on from father to son, we are lacking this skill, and this is a craft which is on the brink of extinction. So the subject of this research is to deal with uncertainty in production and maybe go towards an autonomous robotic stone dresser with a human interaction, of course. It is done under the supervision of Professor Aaron Sprecher at MTRL. This is our lab. It acts as a platform for multidisciplinary collaboration between engineers, designers, scientists, and it engages in development of innovation and fabrication techniques in architecture. We're downstairs at the ground level if you want to see it afterwards. And essentially, our motivation is that design and fabrication tools have always played a crucial role in the process of architectural creation. And the combination of these tools has increased the tool's impact on the formal definition of the object. And this impact is recently evident with the integration of robots into architecture and design. But this notion is not a new one. Some 20 years ago in the Technion and Civil Engineering Department, there were research projects about customizing standard construction. And on the left, you can see an automated crane, and on the right, an assembly robot for floor tiles. And the standard industry, however, AutoCAD number 1 on the left, which we have on a simulator, did not work with these robots. However, in the past decade, we have a very robust integration of robots into design tools, so we can actually connect computer-aided design and manufacturing and use these robots as designers. And in parallel to automation of these standard construction techniques, this mode of exploring also allows to explore non-standard shapes and forms. And this is from our lab. It's essentially hot wire cutting of a foam block, which used to take, with CNC milling machines, some 2 hours. This takes 30 seconds and produces very nice results. However, as digital design exists in a very sterile and precise environment, Not the geometrical data, nor the fabrication process contain any real-world information, and still relies on a very top-down approach to design. You create your code, you upload it to the machine, and it produces an object. So much of our research focuses on exactly developing the opposite, a middleware that is a combination of software and hardware, which enables communication between the robot and different sensors in a manual craft scenario. And this is a brush tool. It's a simple example, but a very efficient one. The brush is connected to a load sensor. Essentially, it feels the pressure it applies on a surface. So you can think of a painter who feels how much weight he applies on a canvas, and it feeds back to the computer like this EEG, and we can actually see how much a painting weighs in kilograms. This protocol applied onto a surface can produce these patterns, and the robot essentially knows exactly how much force it applies on the canvas. It can go backwards. If it applies too much pressure, it could go forwards. If it doesn't apply any pressure, and it can kind of tackle this problem of creating an even line with a very non-standard medium, which is oil paint. Now, aside from touch sensing, we explore the use of machine vision as well to produce real-time robot toolpath. Here, this is Uri. He's a neuroscientist. He controls the robot using hand gestures. And object detection, of course, which allows the robot to detect objects within its sphere and hopefully in the future allows it to detect tools it works with. But going back to the context of stone processing, the advantages of the human expert is achieved by their ability to negotiate with the material and overcome conditions which arise due to the uncertainty inherent to the process. So this is at Gabelski and San's backyard because they hide this guy. They want you to think it's all automated, but essentially they're very relied on. Muhammad, in this case, was their main stone craftsman. Now, in this example, the human eye notices how much material it removed, and then knows exactly where to place the tool in the next iteration. Our research, we talk to these guys, we talk to craftsmen, we interview them, we create protocols, and then guidelines for craft. We use essentially those tools, classical tools, and if you look at the point, flat, and tooth chisel, and look at Michelangelo's with all humility, anyways, you can see the tools applied to the surface. The hair is using the tooth, the face is using the flat, and the point on the rest of the body. And this is applicable to architecture in all scales. So Michelangelo's slave on the right, and Meydan Salah, it's a Nabatean city in the region of Hajj, Saudi Arabia. Essentially, it's the same practice. And it's still used today on concrete. And if you go to Sawaski Library at Tel Aviv University, the whole facade is supposed to create this notion of a sculpture, and they used chisels to create it. Now, what we do in short, and I'll be very fast because I don't have a lot of time, to analyze the motion, we use motion capture techniques from the movie industry. We have Yotam, who's a craftsman. He works in the north. He works for Arco. He's a skilled craftsman. This is in the Viz lab, Daphna's visualization lab. Here at the Technion, we can record the action. We can then reiterate it and put it onto the computer program and reverse engineer the tool. On the side, on the left, you can see a lot of quantitative analysis of the tool. It's not so interesting to view the numbers as it is to transform them onto the robot afterwards. And to complete the task, we created machine vision to detect the material removal. This is done by a simple RGB camera to detect the blobs, essentially the material removed by the tool. We combine all of these into this toolkit, and the toolkit consists of this end effector, which is placed on the robot with the help of some mechanical engineers. We created this. It's made out of 50 components, and essentially it just helps us hold the tool in place while the robot operates it. And when it works, it looks like this. This is the first run. So the autonomy here is received by the fact that the robot waits for a command. It takes a snapshot of the stone. It detects defects within the stone, and it kind of chisels around it, not to deflect any material from any defects within the stone. Now, this was done like a month ago, and the results were not amazing. So we kind of figured out that the problem is we're using only two-dimensional vision. So we went to our friends in the autonomous car division, and they use these cool cameras, 3D cameras, and this is our setup. It's a 3D space, so we use a 3D camera. So this is a point cloud produced in real time by a 3D depth camera. You can see the point cloud. Essentially, there's no stone, it's only points. But these points are very useful, bringing them back to the physical life through this, I'd say, the virtual environment. We inject them back to the virtual environment. We project the points, and we ask the robot to detect the top surface of the stone, removes whatever is clutter. Then we call some points, because it's a lot of information to digest, and we only have the size of a TCP socket to transfer information from the robot and the camera. I'm done with things. And so here we have like some 300 points, which is exactly the amount of information you can transfer, which is 64 Ks in this sense, in this case. So we can think about the new iteration of craft. It's a craft derived out of the size of the communication protocol you have. And this is the pattern we chose to carve out in 3D. It's essentially the pattern created by the computer vision. And somebody talked about safety. This was done very slowly. It just hyperspeed. And this is the second trial. And it starts with a very traditional teletiche pattern, and then it moves on to this other, and this is the object. So this is where we stand today, and we're still in development, and I have another year, and I hope to get more autonomous. Thank you very much.